You're a mechanical engineer, someone who thrives on solving problems and bringing ideas to life. And you love building things, turning concepts into reality, whether it's a simple gadget or a complex machine. But here's a skill that truly sets you apart from the crowd: designing plastic parts with precision and creativity. Look around you. Your phone case, car dashboard, TV remote, even parts of the International Space Station, and countless medical devices are made of plastic. Plastics are everywhere, shaping the world we interact with daily. Mastering plastic design lets you create lightweight, affordable, and complex products used by millions. It's the gateway to innovation in industries from consumer electronics to automotive and healthcare. Plastics are incredibly versatile, flexible like a rubber duck, strong like an engine gear, or even transparent and beautiful like a water bottle. Their adaptability is unmatched. But you can't just swap metal for plastic and expect success. The rules are different and the challenge is unique. Plastics require a different design mindset, one that considers their unique strengths and limitations. You need to understand how plastics flow, cool, and change with temperature. These factors affect everything from strength to appearance. Learning these rules unlocks new design possibilities, like snap fits and living hinges that are impossible or expensive in metal. These features can simplify assembly and reduce costs. This guide is your cheat sheet to becoming a plastic design pro, giving you the knowledge to make smart choices from the start. We'll focus on practical, hands-on tips to help you design real, functional plastic parts that work in the real world, not just on paper. We'll cover common pitfalls, clever tricks, and the key principles you need to avoid costly mistakes and create better products. By the end, you'll have a clear roadmap for tackling your next plastic design project with confidence and creativity. Let's dive in and unlock your engineering superpower. Before picking a plastic, ask, what does this part actually do? Gather requirements. Will it be a cover, a gear, used indoors or outdoors, exposed to chemicals or sunlight? List the loads: tension, compression, impact, and environmental factors like temperature and UV. For example, a power drill handle must be strong, ergonomic, resist sweat and grease, and insulate electricity. Your first deliverable isn't a 3D model, it's a spec sheet. Write down the part's purpose, conditions, lifespan, and cost targets. The more you know up front, the fewer surprises later. When it comes to designing your part, choosing the right plastic is like picking a superhero for your team. Each material has its own unique powers and weaknesses. Your choice will define your part's identity, performance, and even its longevity. Commodity plastics like polypropylene are affordable and widely used for everyday items. But if you need more muscle, engineering plastics like ABS, polycarbonate, and nylon step up with greater strength, durability, and heat resistance for demanding applications. Always consult your spec sheet. If your part needs to withstand heavy loads or impacts, glass-filled nylon is a great option, offering enhanced strength and rigidity. Need your part to be see-through and tough? Polycarbonate is your hero, facing extreme temperatures or harsh chemicals. Consider high-performance plastics like PEEK, which can handle the heat and stress. Remember, don't over-engineer by choosing expensive materials for simple jobs. But also don't cut corners with cheap plastics where strength and reliability matter. Balance is key to avoid costly failures. Always review technical data sheets and talk to your suppliers. They can help you navigate the options and avoid common pitfalls. For something like a power drill handle, you want a material that's tough, rigid, and cost-effective. Glass-filled nylon or a PC-ABS blend are both excellent choices, providing the right mix of strength and value. Carefully match the material's properties, like impact resistance, flexibility, and temperature tolerance, to your specific requirements for the part's function. Don't just settle for black plastic. Be precise about the resin and grade, because the details make all the difference in performance. Take the time to research, compare, and select the best material for your needs. Wise choices now save headaches later. In the end, the right material is the foundation of a successful, reliable part. Just like a superhero, it's what keeps everything together and performing at its best. With requirements and material set, it's time to pick a manufacturing process. Injection molding is the go-to for high-volume, complex parts, fast and cheap per part, but molds are expensive. Blow molding is for hollow parts like bottles. Extrusion for long profiles like pipes. 3D printing for prototypes or low-volume complex shapes. Your process choice shapes your design rules. Sometimes the part dictates the process. Sometimes the process dictates the part. For a TV remote housing, injection molding is perfect for millions of units. For a custom bracket, 3D printing is fast and flexible. Match the process to your needs and budget. The right process makes your design possible. When you're ready to design your part for manufacturing, it's crucial to think ahead. Let's use injection molding as our example, since it's one of the most common methods for producing plastic parts at scale. Rule 1. Always keep your wall thickness uniform, ideally between 1.5 and 3 millimeters. This consistency is key for ensuring the part fills properly and cools evenly during molding. If you have thick and thin sections, you'll likely see warping, sink marks, and other defects that weaken your part and make it look unprofessional. Instead of making walls thicker for strength, add ribs. These thin, vertical supports reinforce your part without causing molding issues. Rule 2. Add draft angles of 1 to 3 degrees to all vertical walls. This small detail makes a big difference, allowing parts to eject smoothly from the mold without sticking. Without draft, parts can get stuck, leading to damage, wasted material, and costly delays in production. Rule 3. Avoid sharp corners. Use fillets with an inside radius at least half the wall thickness to reduce stress concentrations and help the molten plastic flow more easily into every part of the mold. These 3 rules, uniform walls, proper draft, and generous fillets, form the golden trio of plastic part design. Mastering these basics puts you well on your way to creating a reliable, high-quality plastic part that's easy to manufacture. Ignore them and you'll run into defects, production delays, and extra costs that could have been avoided with good planning. So, always design for manufacturing right from the start. Don't leave it as an afterthought. This approach saves you time, money, and a lot of headaches down the line, making your entire process more efficient. Get these basics right, and your part won't just work. It'll stand out as a true winner in both performance and manufacturability. Most plastic parts are part of a bigger assembly. Designed for easy assembly, think about how your part connects with others. Snap fits are a clever way to join parts without screws or glue, but they need careful design to avoid breaking. Bosses, hollow cylinders, are for screws or pins. Keep wall thickness uniform and add fillets to prevent stress. Living hinges, like on a tic-tac lid, are great for flexible connections, but only work with certain plastics and careful design. Smart assembly features save time and money on the production line. Is your part strong enough? Time for structural analysis. Use finite element analysis, FEA, to simulate loads and spot weak points before making molds. Plastics behave differently than metals. Properties change with temperature and time, and creep can cause slow deformation. FEA helps you find and fix problems early, but always confirm with real-world tests. Iterate, tweak your design, rerun simulations, and improve. Digital testing saves time and money. Make sure your part survives real-world use. Design and simulation are done. Now make it real. Start with 3D printed prototypes to check fit, feel, and assembly. Test for ergonomics and function. Find issues you can't see on a screen. Refine your design, then move to higher fidelity prototypes, CNC machining, or soft molds for small batches. Test for strength, chemical resistance, and temperature durability. Validate your FEA results with real-world abuse. Iterate, build, test, learn, and improve. Your first prototype won't be perfect. Embrace feedback and keep refining. The cycle of prototyping is the heart of great engineering. Keep learning, keep building, and go create something awesome.